Welcome back, students. Myself Manjunath, Math Guru. So today I taken the topic on mechanical springs. Don't forget to share, subscribe, comment on my channel. Like, share, subscribe, comment on my channel, Math Guru. Okay. So first, let me give the design procedure of helical springs. So yeah, first things first, let me write the step by step. F is the given load, spring index is C, deflection is Y, small y, allowable shear stress is tau, then rigidity modulus is G, so the step number 1, design of wire diameter. Shear stress tau equals 8 FCK upon pi d square, where K equals curvature factor. All these equations are readily available in the design data. You can either refer Balveer Reddy or Lingaya for VTU, and whatever reference book you refer, the procedure is the same. 4C, okay, let me write it here. C minus 1 upon 4C minus 4 plus 0.615 upon capital C. So what we do is we'll find the D. For that you'll refer table, okay, substandards, then select standard wire dia according to the standard which is we have got. So first we'll be finding D. Okay, we'll discuss how we can go ahead with the this one. What is that procedure when it comes with the problem? Okay, for time being, just refer to the steps what I'll be telling. Next, second step is mean coil dia. That is capital D equals excuse me, equals C into D inside dia of coil equals Di equals capital D minus D Similarly, outside eye of coil, capital D O equals capital D plus D. So next step, will be the deflection. Deflection small y equals 8 capital F capital D power 3 small I products upon G D power 4. Okay, so here you'll find the deflection y. Find the deflection y if number of coils is given. Okay, that is I is given. So, or find the number of coils I for that also if deflection is given. So this also you can use, this also you can use. Both equations are given separately. You can actually, if you have this equation, you can derive from this. You will come to know when we solve problems. So next step 4. Free length of spring. See, why I am referring this, I am actually referring the design data handbook. So you should know how to use the design data handbook, then only you will be able to solve the problem, because all the formulas cannot be remembered in the mind. Everything is readily available in the data handbook. Only thing you should know how to use it. So this is L0 greater than or equal to, so I plus N into D plus Y plus A, where I is number of active coils, N equals extra number of coils depending on conditions, end conditions. Then so we have three conditions: equal to 0, equal to 1, equal to 2. So this for 0, N will be 0 for plain or free ends, and 1 for squared or ground, and it is for both 2 for squared and ground. Next, okay, so always we recommend for good design, we'll go with N equals 2 square and ground ends, and also we have small a equals 0.25 into y. This is your clearance between coils. We always give 25% clearance of deflection. Okay, remember that. Next step will be pitch with respect to a figure given. Small p equals L0 minus 2d upon I. This is for square and ground. So these assumptions can be made suitably. Then if we go for plane ends, this is the equation, and for ground ends only and last one for L0 minus 3d upon I for square ends. Okay students, then step 6 will be stiffness. F0 equals F upon Y. In step 7, the last step, length of wire required to manufacture the spring. Now students, will consider one problem before that. Yes, so this is LW equals pi d I dash. Okay, I dash is total number of coils. I dash equals I plus N. So when we substitute, we get LW equals pi d into I plus N. Okay, that is the procedure. So 7 steps. So straight away we'll get into the problem. And problem is considered based on this. So let me write the question. So design a helical compression spring to sustain an axial load of 3 kilonewton. The deflection is 60 mm. Spring index is 6. Shear stress is not to exceed 300 MPa. Rigidity modulus for the spring. Material is 81 MPa. Sorry, it is GPa, gigapascals. Okay students, so friends, let us solve this problem step by step. Let us write what's the given data. Given data, we have load is 3 kilonewton, so capital F equals 3000, 3 into 1000 Newton, which is 3000 Newton. Then there is your axial load. What else is given, student? Deflection. Okay, deflection Y equals 60 mm small y. Then we have spring index capital C equals 6. Then we have shear stress tau is not to exceed 300 MPa. 1 megapascal, you know that it is equal to 1 Newton per mm square. rigidity modulus capital G equals 81 gigapascal, which is 81 into 10 power 9 Newton per meter square. So this will be 81 into 10 power 3 Newton per mm square. So that is the given data F, Y, C, tau and G. Okay students, then next what we have to do. So as usual we will go with the shear stress. If this conversion is not clear, or you can write Newton pascals, or this is fine, whatever I have written megapascals, express everything in megapascals. You can keep this in megapascals, because 1 giga equals 10 power 9 pascals equals 10 power 3 megapascals. Okay, hence I have written there into 10 power 3. Okay, MPa also you can write. So I'll write here 1 MPa equals 10 power 6 Newton per meter square, that is equal to 1 Newton per mm square. This in units conversion is very important when it comes to SOM or design subjects like that. Make mistakes with the units, then everything will become like it will become a mess. You will end up, will not get marks suitably, it will go off, it will cut marks. So be careful. So now as usual the first step is to find the tau. So let me write that. Tau equals, for the equation, 8 FCK upon pi d square. So I already told you also, this equation is usually used for finding d. So here, before the d, let us check whether we have, do we have all the parameters. So tau on substituting, it is 300 here, equals 8 into capital F equals 3000, and capital C equals 6. Now to find K, okay, pi and d square, we don't know K, but for K there is again a formula. Just leave it like that, call that as equation 1. So for K the formula is 4C minus 1 upon 4C minus 4 plus 0.615 upon C. Okay, if you look at the beauty of the substitution, student. Now I'll show in front, okay, how to do the substitution in calculator. So just take this as, okay, you can just observe what I'm trying to do here. 0.461. So yeah, okay, I'll put it here, or I'll keep it here. Okay, yeah, one second. Yeah, 4C minus 1. I'll do one thing, I'll write this equation somewhere down, okay, or else I'll just check out what I'll do. See, I'll just click on, okay, I'll clear everything so that there is nothing, it is starting fresh. Okay, so this will be, I'll just delete this. So observe whatever I'm inputting here in the calculator. So first thing first, here observe here whatever I'm inputting. So that will be 1 second. Let me just minimize that. Okay. Yeah. Excuse me. Okay. So this will be excuse me, students. So